Okay, so everything that you see in red is a property that I got or something that I calculated. Let's see if this looks, get rid of the glare here. Might look better. You might pause it if you need to write the values down. But basically, we calculated T2. From that, got U2. We knew T3, so we looked up U3. We calculated T4. From that, we could look up U4. We knew T1. We could calculate U1. Based on that, we calculated Qin and Q out. With Qin and Q out, we calculated the efficiency. Not too bad. All right, I'm going to erase this, and we'll see what happens when we do variable specific heat. So we'll do the same problem, just see the effect of the different assumption. Let's see. So all this is the same. This is going to change that. So it's going to change. This equation no longer applies because it was based on the assumption that specific heat was a constant. So I need a new T2, and that's going to affect U2. T3 is still 1,000 degrees, so that's good. Let's see. Q in and Q out are going to be affected. So this number is going to change. Same thing over here. This equation no longer applies. T1 is still the same, but we need a new T4. All that changed. All this changed. This equation is no good. We didn't even use that last time anyway. All right, I think that's it. So we get to the point here where same governing equations apply. We're looking for efficiency, which depends on net work and Qin. Net work we can write as Qin minus Q out. We figured out that we couldn't deal with it on an absolute term basis, so we're going to divide everything by mass. And that's where this equation came from. So now we have equations for Q in and Q out that depend on U1, 2, 3, and 4, which depend only on temperature 1, 2, 3, and 4 because this is an ideal gas. If you go all the way back to think of what internal energy means, we said it was sensible energy, chemical energy, latent energy, and nuclear energy. Well, we're not changing the phase of this ideal gas. We're assuming that air is the working fluid. It's not undergoing any chemical reactions, so the only thing changing is sensible energy. So that's why these internal energies are only affected by temperature and not pressure. That's why we only need the temperature to look these up, because it's only a change in sensible energy. All right, variable specific heat, ideal gas, isentropic process. We have two equations. We want the one with volume, so we can look up this. V2 over V1 is VR2 over VR1. If we could solve this for VR2, V2 over V1 times VR1. V2 over V1, that's 1/7. So that's the inverse of this. So 1 over 7 times, now we'll go get a number for VR1, put it in here. That's going to get us VR2. Based on that VR2, we're going to know T2. Based on that T2, we're going to know U2. Same thing over here for the isentropic process from 3 to 4. Remember, these equations only work for an isentropic process. So that's 1 to 2 or 3 to 4. Don't try to write it from 2 to 3 or 4 to 1. So VR4, V4 over V3 is VR4 over over VR3. We're interested in VR4. That's what's going to tell us T4. That's the temperature we need. So VR4 is V4 over V3 times VR3. All right, V4 over V3 is 7. Now we'll go look up a number for VR3. We'll get that in table A17. Based on that, we'll have VR4. Based on that VR4, we will have T4. And based on that T4, we can look up U4. Once we have U2 and U4, we have U1 and U3. We can go back through these equations and get to the efficiency.